We are asked to find the volume of a solid whose base is the region bounded by y equals x squared, the x-axis, x equals 0, and x equals 2. And to form that solid, we're going to use cross-sections taken perpendicular to the x-axis. And we're going to use the following shapes, and it looks like we're going to do squares first. So take a moment and graph that on your own. And when you do, you would get this graph. So here we have y equals x squared. Here we have x equals 0. Here we have x equals 2. And here we have the x-axis. Now, I want you to picture a solid. We're going to start with squares whose cross-section is perpendicular to the x-axis. And this is the figure that we're going to get. Now, this length is going to figure prominently in our discussions going forward. So it's so important that once you have your graph set, once you have your cross-section drawn perpendicular to the x-axis, you need to get this length. Okay, so what is this length? We see that we're dealing with dx. That means any integration we have is going to have dx in it, which means the integrand is going to have x's in it, which means everything should be solved for y. Okay, so we want to make sure we have y equals in any graph that we're talking about. So here we already have y equals x squared. That's this graph here. This x-axis is y equals 0. Okay, to get the length of this, we're talking about y values. So our y values are going to be y equals x squared and y equals 0 on the top and the bottom respectively. So if we do top minus bottom to get this distance, we're going to be dealing with y equals x squared and y equals 0, and when you subtract them, you're going to get this distance as equaling x squared. And you're going to see how that becomes vital information in the next few moments. Next, let's try to graph this with a little bit of perspective. So the first thing I think that makes this easy is to take this y-axis and rotate it. I don't know how many degrees that is from this line to that, maybe 60 degrees, and then draw another xy axis. Now, folks, literally turn your head, put your right ear on your right shoulder, and just redraw this graph and try to maintain the same relationships. So here we go. We're going to take this and draw y equals x squared, like so. And we're going to drop a perpendicular straight down. And we're trying, as we draw this, to keep that parallel to that, as in the original drawing. Now we're going to draw our little rectangle. And again, as we draw that, we're going to try to keep this parallel to the y-axis. All right, so that gives us the base that we were talking about over here. Now, we already have that length. We figured out that that length is going to be x squared. Now, folks, what we're going to do is we're going to bring squares up and out of the screen, straight up to the ceiling. All right, and we're going to make that length equal to the base length because we're dealing with squares. All right. And these squares are going to have a little thickness of dx. So let's draw that in. Okay. So that is an example of a square that's coming up and out of the screen, going straight up to the ceiling. Now, the way to do these problems is to get the volume of this one tile, if you will, because this now has a thickness to it. So I'm going to call this a tile. All right. It looks something like this. You have a square face You have a square face that has thickness to it. Now the idea is to get the volume of that one tile. So to get the volume of that one tile, we're going to need the area of its face taken through a distance of dx. The area of the face is 2 dimensions, and then the third dimension is that width. So moving to this diagram, the area of this face is 2 dimensions, and then it's taken through space, a thickness of dx, to give us the third dimension. So if we can get the volume of this one tile, then we can do a summation in the form of integration to get the volume of the entire solid figure. Okay, so how do we get the area of that face? Well, it's just the length times the width. And because this is a square, they are both x squared. So let's go ahead and set up our integral. Remember, if we're dealing with dx, that means our starting and ending point are going to be x values. So you can see we're summing up from x equals 0 to x equals 2. These have to be x values if you have a dx. So now, folks, we have length. Here's our 3 dimensions for volume. Length times width to get the area of the face, and then it's taking through a distance of dx. This is 2 dimensions. Add another dimensions, 3 dimensions. This is the volume of one tile, and then we're going to do a summation. Recall the integral symbol is a hidden big S. That means summation, and that's going to give us the volume of the entire region. Next, we are asked to use semicircles as our solid figure to create volume. So here we're going to take our y-axis this time and rotate it counterclockwise about 45 degrees, and that's going to give us this y-axis. Now I'm going to turn my head to the left such that my left ear touches my left shoulder, and I'm going to recreate the same relationships. Here's my y equals x squared. I'm drawing this with my head tilted. I'm going to draw the line, the vertical line, x equals 2, and I'm going to make sure I'm parallel to the y-axis. Then I'm going to go ahead and draw in my base, and I'm going to try to create a semicircle that comes up and out of the screen, up towards the ceiling. And to do this, I find it's easier to create like an arch, almost like the Arch of St. Louis. And then we'll try to give it a little thickness and see if that works out. Okay, so this is coming up and out of the screen towards the ceiling. Now, the same thing applies here. This is a semicircle that has thickness to it. So the whole idea, folks, is to get the area of that face of the circle. In this case, it's a semicircle. And once we get this area, we're going to take it through space, that distance. So the area is 2 dimensions. Taking it through a width of dx gives it a third dimension. Okay, so let's talk about how to get this area. So the whole key to get the area of any circle is to get its radius. Now, if you look here, you could see that this distance here, that again, as I mentioned very early on, is going to feature so prominently in every one of these problems. This distance here, which is x squared, is the diameter of this circle. If you imagine this circle extending this way, this is where the center is. I don't know why I have a dot there. Let me get rid of that. That is distracting. Okay, so that's our circle. So that's the diameter of the circle, but we're only dealing with a semicircle. So we have to recognize that while the diameter of the circle is x squared, we want its radius, which is going to be 1/2 x squared. So to get the area of the circle, if it was an entire circle, would be pi r squared, which means we're going to do pi times x squared over 2 squared. But then, since it's a semicircle, we're only going to take 1/2 of this. All right, so it's a little bit complicated of a formula. So let's see, I have this written out up here perhaps a little bit more neatly. But again, the concept is that the base length is the diameter. We need to take half of that to get the R for our formula. And then once we get the formula for the, not sure where to put this. Once we get the formula for a circle, we got to take half of it. So we end up having radius is half the diameter. The diameter is x squared. Half the diameter is x squared over 2. Pi r squared would be an entire circle. We're only taking half of that because this is a semicircle. And when you do your math, this is what you come up with. We are going to set up the integral. And in this video, we're not going to compute these definite integrals because to me, the whole skill to these problems is the setup. So we're going to integrate this function, which is the area of the face of that semicircle times dx. So this is 3 dimensions. This is a volume of one of these. One of these tiles is going to have this volume. And when we take one of them, the volume of one of them, and we do a summation from x equals 0 to x equals 2, we get this integral, and that will give you your volume. Next, we are asked to create rectangles that have a height 3 times the length of the base. So we're going to go ahead and draw our perspective, and then we're going to draw rectangles coming up out of the screen. And this is what we're going to get. Again, I rotated this y-axis 45 degrees counterclockwise. I'm turning my head to set up this pink axis and curve. Here's my rectangle coming straight up out of the graph. Now notice, this height is 3 times the base length. Again, that base length figures in every one of these problems. So if this height is 3 times the base, it's none other than 3x squared. To get the area of this face, we're going to do the base times the height. That's x squared times 3x squared, or 3x to the 4th. In order to get volume, we're going to take the area of that face and take it through a distance of dx to give it a 3rd dimension. Therefore, the volume of this one tile is going to be 3x to the 4th dx, and to get the entire figure, we're going to do an integral as a summation of all these tiles from x equals 0 to x equals 2. Next, we are asked to use equilateral triangles as our figure. So in this case, I rotated the y-axis clockwise about 45 degrees. I'm turning my head such that my right ear is on my right shoulder. I again draw this green setup, maintaining the relationships. Here's our equilateral triangle. So folks, as always, our goal is to get the area. Our goal is to get the area of that face, which now is an equilateral triangle, and then we're going to take it through space a distance of dx right here. Okay, to get the area of an equilateral triangle, there is a formula you can memorize if you'd like. I'll go into how to derive it very quickly, but that is the formula. So here in this problem, our S is going to be x squared, the length of the base. To derive this formula very quickly, you have to recognize that equilateral triangles all have an angle. Each angle is 60 degrees. So if you drop a perpendicular, we need the height, because the area of a triangle is 1/2 base times the height. To get that height, we recognize that this is now a 30, 60, 90 degree triangle. We have the side opposite the 30 as 1/2 the base, or 1/2 s. To get the side opposite 60, we're going to multiply by the square root of 3. So that gives us a height of square root of 3 times 1/2 s. Once we have our height, we can do 1/2 base times height, And that's how you get s squared square root of 3 over 4. In our case, our s is already a quadratic, so when we square it, we're going to have something to the 4th power. And here it is. This area would be for 1. This would be 1 triangle's face. We would multiply that by dx to get the volume, and then we would do a summation to get the volume of the entire solid. Next, we're asked to use an isosceles right triangle with the hypotenuse as the base to create our solid figure. So let's go ahead and draw that. Okay, and there's our isosceles triangle. Now folks, because we're going to have to find the area of that face, I want to review how to navigate a isosceles right triangle with respect to the sides. So an isosceles right triangle is none other than a 45, 45, 90 degree right triangle. So here we go. Because those sides are the same, then that means these angles, the base angles, are the same, so we have a 45, 45, 90 degree right triangle. And here's the model to remember. 1, 1, square root of 2. So let's say you have the length of the side opposite the 90 degree angle. Okay, we have that. And we're trying to find this value, which is the side opposite the 45 degree angle. When you move from a side opposite the 90 to the side opposite the 45, you're going to get smaller. So here is our scale factor, square root of 2. If you're getting smaller, you're going to be dividing by the square root of 2. Okay, conversely, let's say they give you the side opposite the 45 degree angle. Let's say that is 12. And you're trying to find the side opposite the 90. So in this case, we have the 45 degree side, that's 12, and we're trying to find the side opposite the 90 degree, that's why. Here is our scale factor. Because we're going to get bigger as we move to the side opposite the 90, this is going to be 12 multiplied by the square root of 2. Let's now talk about how to get the area of this face in this isosceles right triangle. Okay, the only thing we know right now is that that base is x squared. So if the base is x squared, we also know these are 45 degree angles. Okay, so we have the side opposite the 90. If we want the side opposite the 45, we're going to get smaller by a factor of the square root of 2. So both of these are going to be x squared divided by square root of 2. But folks, to get the area of this, we need this height. We have to do 1/2 base times the height. So how are we going to figure that out? Well, now we have, by dropping that perpendicular to get the height, we've created two new 45, 45, 90 degree triangles. So here's our 90 degree. This is 45. This is 45. Okay, so how are we going to get this height? Well, we have the side, in this particular triangle here, this smaller triangle, we have the side opposite the 90. What is that? Let's work here in green, up here in the right-hand corner. So we have the side opposite the 90 degree. Look, there's your 90 degree angle. There's your value, x squared over square root of 2. We're trying to get the height. The height is opposite the 45 degree angle. So how do we get from a 90 to a 45? We're going to get smaller, so we're going to have to take that x squared square root of 2 and divide by square root of 2. So when we do that, folks, we get the following for our height. We get x squared over 2. So this becomes our height right there. And since this is a 45, 45, 90 triangle, If this is opposite the 45 and that's the opposite the 45, this becomes x squared over 2 and that becomes x squared over 2. So folks, the summary of this is that when you have a isosceles right triangle and you end up dropping a perpendicular down here, all three of these are going to be 1/2 the base. So this is going to be 1/2 the base, x squared over 2. This is going to be 1/2 the base, x squared over 2. And the height is going to be x squared over 2. Okay, that got a little blurry there. Okay, let's now go back to our problem. We're still trying to find the area, but the good news is now we got the height. We always had the base. So let's go ahead and formally do our area computation. That is done here. Right. Here is our base in pink, 1/2. It's 1/2 base times the height, and when you do the math, you're going to get x to the 4th over 4th. For the area of the face, the volume is going to be multiplied by dx, and then to do a summation for the entire region, we're going to take the integral from 0 to 2 of x to the 4th over 4 dx. Next, we are asked to find the volume of a solid whose base is bounded by a circle with the center at the origin and a radius of 3. And again, we're going to use cross sections perpendicular to the x-axis, and we are going to look at various shapes, perhaps. Okay, first thing you want to do is draw a diagram of this radius and put in the base. So let's go ahead and do that. The formula for a circle, recall, is x minus h squared plus y minus k squared equals r squared, where h and k are the x and y coordinate respectively of the center. Here the center is 0, 0, so we're reduced to x squared plus y squared equals 9. Now, we're using a rectangle, a base perpendicular to the x-axis. That means dx is involved. If dx is involved throughout this problem, we are going to be integrating with a dx in the integral, and therefore the integrand has to be in terms of x. Therefore, we're going to have to solve for y. The other reason to solve for y is to get this length, which is very important in all these problems. We need y values. We need the y value here minus the y value there. Therefore, we need everything in terms of y. Okay, so let's go ahead and draw this in 3 dimensions. So here is our 3-dimensional representation of our figure, and we're going to use a square in this example. So again, I've rotated the y-axis clockwise 45 degrees, and when I draw this circle, I tend to do it more like an oval. I'm not sure why, it just gives me a little bit more perspective. I take the base here, which we have on our original diagram located here, and I extend perpendicular up into the air and create a square. The goal, again, folks, is to get the area of this face. This area is a square, therefore the base is going to equal the height. Recall that the length of the base is going to be this y distance. So it's the y value on the top minus the y value on the bottom. The y value on the bottom is negative. Let me write that in here. This is negative square root of 9 minus x squared. And the top version is positive 9 minus x squared. So when you do top minus the bottom, these two minuses turn into a positive. So our entire length of that base is going to be 2 times the square root of 9 minus x squared. Okay, here's our base length depicted up here. It turns out to be 2 times f of x. So the other way to do that is to recognize that this is f of x here, and the entire length is going to be twice that. Here's our base. Our area is going to be length times width. In this particular case, the length, the base, and the width, however you want to say it, are both the same. Therefore, you're going to get this expression squared. That's going to lead to 36 minus 4x squared. So the volume of one tile is going to be the area of that face times the width, which is dx. And when we do our integral to get the volume to sum it up, we're going to go from x value of -3 to x value of +3. Again, that value matches whatever the d is. We have dx, that's an x, and we have x's inside the integrand. Next, we are asked to examine the region bounded by this parabola, x squared minus x minus 3, and the line y equals x, and we're asked to draw figures with their base perpendicular to the x-axis. So here's an introduction to this problem. Here's our base that's drawn perpendicular to the x-axis. Therefore, we're going to be using dx. If we're going to be using dx in this problem, we're going to be integrating with respect to dx. That means we need x's within the integrand. That means we need x values here. So let's first determine what these x values are. So we have two functions. We have y equals x, and we have y equals x squared minus x minus 3. We want to end up with x equals something. So that means we want to keep the x's involved. So what we're going to do is we're going to set, if we have y equals x and y equals x squared minus x minus 3, we're going to set these equal to each other, and then we're going to solve for the x that makes that true. So here we've gone ahead and done that ahead of time. Let me just blow this up. And here we have that calculation. So we have x squared minus x minus 3 equals x. We go ahead and we factor, put everything on the left side, and we get x equals 3 and x equals -1. So that is how we get our beginning and end to our integrals for these problems coming up. Okay, so let me go ahead and put x equals -1 here and x equals 3 there. Okay, the next thing we need to determine is, what is this distance? What is the distance of that base? Because that distance is going to figure prominently in all of these problems. So this distance is a y distance, and we're going to use top minus bottom. So if we want to figure that out, we're going to have the base is going to equal the top function minus the bottom function. So that's going to end up being this right here. How did we get that? This is how we got it. Let's blow this up. Okay. Remember, we want to end up with a length that's in terms of x. We want x's in our integral. So here we're going to say that this value is going to be x. That's the height there. This height here of the function is going to be x squared minus x minus 3. So we're going to do top function, which is x, minus the bottom function, which is x squared minus x minus 3. And when we distribute that negative, we're going to end up with a base length shown here. We are now asked to use semicircles to create a solid figure and then determine that figure's volume. So folks, the first thing we need to do is to determine the surface area of that semicircle, and then we're going to take it through space a distance of dx, and that's going to give us the volume of that one semicircle tile, if you will. Then we're going to integrate across this interval. Now, let's look at what we have here. If we want to get the surface area of that semicircle face, look what they've given us. They've given us the diameter. So we need to take 1/2 of that. So here's going to be the game plan. The area of an entire circle is pi r squared. We only want 1/2 of that because we're dealing with this semicircle. So we just want this part of it. So we are going to be dealing with 1/2 pi r squared. Now, they gave us the denominator, the diameter. The diameter is this base right here. So we have to take 1/2 of the base and use that as our radius and square that. So that's the game plan here. Okay, let's go ahead and blow this up a little bit. Okay, so here, this is basically what I just reviewed. We have an area is a full circle is pi r squared. We're going to use 1/2 of that. The diameter is the base. So therefore, the area of one semicircle, the surface area, is going to be right here. So here is 1/2 pi r squared, where the r is the diameter divided by 2. So folks, we're going to take this area, multiply it by dx, and then integrate that to get a summation. And when we do that, we get this down here in green. We go from -1 to 3 because, again, we're dealing with dx. We want x values in our interval. And here's the formula for one tile, 1/2 pi r squared, and then multiplied by the width of dx.